Hi and welcome back to Miles Maths. Today we're just going to look at the transformations of trig graphs, and the first thing we're going to consider is the knowledge you'll already need to have. You must know what your trig graphs look like. If you don't know this, I really suggest that you go away and revise this before we go any further. So here's y equals sine x. We notice it goes through 0, 0, at 90 it's at 1, at 180 it's back at 0, at 270 it's at -1, it goes back to 360, and this graph repeats forever in both up from all the way to infinity and down to minus infinity, with the same pattern, a repeating pattern every 360 degrees. Similarly, cos x, similar graph to sine x, except that it starts at 0, 1, and then goes to 90, 0, and so on, but it's a similar pattern to sine x. You will have done these, and you can look these up under a separate video if you want to. And then tan x, which is the quite unusual one. Tan x, of course, is asymptotic. Asymptotes being lines that the graph approaches but never quite reaches. We can see here that there would be an asymptote at 90. And that the graph would get closer and closer. The graph of tan x would get closer and closer to 90 as it went off in the positive y direction, but it would never quite reach 90. It would never quite touch that line, and then it magically appears on the bottom of the graph, very close to 90, but not quite touching it, and passes up through 180 degrees, and then continues and approaches another asymptote at 270 degrees, and so on. If you don't know what these graphs look like, you need to go and learn them. It is very, very important under GCSE conditions, looking at what those three graphs look like, sine x, cos x, and tan x. You must have those committed absolutely to memory. Oops, turn those two off so you can see tan x again. Good. So let's consider what's 3 sine x is going to look like, and just look at the transformations of these graphs. The way, and I shall do some worked examples for you in a moment that we will do these, is go and sketch what sine x looks like. Just put it in very lightly in pencil or as a dashed graph, or something you can rub out easily afterwards on your exam paper, remembering on your exam paper you will do everything in pencil. On the video I will do it in pen just because it shows up better. So what does 3 sine x look like? Well, the 3 is outside of the function, so this is a stretch in the y direction. So I would take this point at 91 and I would move that to 93. I would take this point here at 180, 0, and that would stay where it was because 3 times 0 is 0. I would take this point at 270 minus 1, and this would become 270 minus 3, and this would stretch, and it would end up looking like that. So there's our graph of 3 sine x. If, on the other hand, I was considering a y equals sine 0.5x or a half x, this would appear to be a stretch, which is good. The stretch is inside the function, so this is going to do the opposite of what I expect, and it's going to do it in the x direction. So now what I'm expecting to happen is I'm not expecting a stretch of scale factor a half, I'm expecting a stretch of scale factor 2. It's going to do the opposite to what I expect. It's not going to halve it, it's going to double it, and it's going to do this in the x direction. So what I'm now expecting is that this point here at 180, 0 will become 360, 0, and at this point here at 91 will become 181. So I'm expecting this graph to kind of do a massive loop like that, and let's have a look at what happens, and there it is. So we can see that's true. 90, 0, it's become 180, 0, and at 91 it's become 181, my apologies, and at 180, 0 it's become 360, 0. So let's look at this next graph, cos of x minus 30. So we'll start just by sketching. When we do this, as you see on paper, we'll start with cos of x minus 30. We'll start like that, and sorry, just cos of x, y equals cos of x. And now what we're going to do is we're going to think about what the minus 30 does. Is it in the x direction or the y direction? Well, it's inside the function. It's being cosigned as well, so it's inside the function, and it does the opposite of what I expect. if you go and look the summary video, it's going to be 30. So this is not going to be 30 left, it's going to be 30 right. So this is going to take this point here at 0, 1, it's going to move it to 31. It's going to take this point at 90, 0, and it's going to take it to 120, 0, and so on. And all we're going to do is put in all the individual points when we do a worked example of this, but we're going to see this whole graph move 30 degrees to the right. If we then consider something slightly more difficult, something like tan x, and we look at tan x minus 20, well, the same thing happens. What does the minus mean? The minus means it's inside the function to begin with, sorry. So we're inside the function, so we're going in the x direction. And we're doing the opposite of what we expect. So we're going to be going 20 degrees to the right. So this point here at 0, 0 will end up at 20, 0. This point here at 180, 0 will end up at 200, 0, and so on. And the asymptotes would obviously move from 90 to 110. They would all move to the right as well. So I can now put that in, and you can see exactly what that looks like, and I would just draw that in, label it, and I would rub out the original graph if I was doing this in pencil on an exam paper. So finally, let's consider this example down here with y equals cos x plus 40 minus 1. Here we have two transformations. It doesn't really matter which order we consider them in. Let's think about what this plus 40 does. This plus 40 is inside the function. Again, you notice I've put cos x on to begin with. This is inside the function, so this tells me that I'm going 40, and it's plus 40, which tells me I'm going to the left because I do the opposite of what I expect. So here at 90, 0, this is going to be 50, 0. Here at 180 minus 1, this is going to become 140 minus 1, and so on. So I'm going to move that all 40 places to the left. However, this also has a minus 1 on the end, which means that in the y direction, I'm moving this graph minus 1. So I'm going to move everything down 1 as well. So I'm now going 40 to the left and 1 down. So when we look at the entire transformation, I'm going to take this point here at 90, 0. I'm going to go 10, 20, 30, 40. I'm going to go to 50, and then I'm going to go to minus 1. I'm going to plot a point here, and I know I'm going to go through that point. So that point will have become that point. I'll take this point here, and I'll go 10, 20, 30, 40. So we'll go to, what's that, 140, and then I'll go down 1, and I will place that at minus 2. And I'm just going to sketch those points in and then join them up. And that's what my graph would look like. And that's how I'm going to do these sorts of problems. So now go and have a look at some worked examples on paper.
Okay, we're going to look through some worked examples on transformations of graphs using trig functions. I'll put the link to this to the examples that I'm using at the bottom of the video so that you can download that if you want to. So let's have a look at this first question. Sketch the graph of y equals sine x minus 1. Well, firstly, we need to know what sine x looks like. So let's just have a think about that. We know it goes through the origin. We know at 90, it's at 1. We know at 1, 50, 60, 70, 80, it's at back at 0. And we know at 270, it's at minus 1. It's really easy to make mistakes with this. And then 360, we're there. So we know that sine of x looks something like this. They've given me a nice little thing to sketch it on, so that's great. That's not the graph I want, though. I want sine of y equals sine x minus 1. Well, we can see that this negative one is outside the function. That means that this is in the y direction, and it's negative 1, so it's obviously negative 1. It's one place down. We've transformed this via the vector 0, minus 1, if you prefer that. So this point goes to here, and this point goes to there, there, and this point goes to there, and this point goes to there, and this point goes to there. And the easiest way is just to put the points in, and you can now see what it looks like, and we'll now just sketch that in rather badly as it happens. Now, in a GCSE exam, you would do this in pencil. You would not do this in pen. However, I'm doing it in pen mainly because pen shows up better on the video. And I would label it y equals sine x minus 1. There's no doubt as to which graph I'm meaning. But you notice I did sine x first because I know what sine x looks like. So let's have a look at a second example. Sketch the graph of y equals 3 cos x. Okay, so the first thing we want is cos x. Well, I know cos goes through 0, 1. I know at 90 it's at it goes through 0. I know at 180 it's down here. I know at 270, 270 we're back there again, and then at 360 we're up there again. So let's just sketch this in, just dotted. Look at that, lovely. And there's a beautiful looking sketch of y equals cos x. But that's not what I'm asked for. I'm asked for y equals 3 cos x. Well, I look at that 3 and I see that it's outside the function, so I know this is in the y direction. So now all I've got to do is take each one of these points and multiply it by 3, because I know it's a stretch in the y direction. So 1 becomes 3, so I'm going to there. 0, 3 times 0 is still 0, so I'm going to go through that point. This becomes minus 3 and comes down here. 1 times minus 3 is, 3 times minus 1 is minus 3. And once again, oh, wrong place. 1 times 3 is 3, so we're back up here. Ignore that cross. And now I can just sort of sketch this in, so I've got to come down like that, through there, back up. Okay, so again, not a very most beautiful sketch in the world. They don't have to be. Y equals 3 cos x, label on my graph, done. There's my sketch of y equals 3 cos x. I haven't gone through plotting every point, but what I have done is I've plotted the most critical points on the graph. Here's another one. Sketch the graph of y equals cos x minus 20 plus 1. Ooh. Okay, so now I've got two different transformations in here. I can see their translations, both of them, but we're going to have to consider these in turn. So the first thing I'm going to do is I'm going to put on cos x the way I did before. So cos looks like 80 minus 1, 270, 360. Make sure it's 360, not 350. It's just so easy to make a mistake there because the way the graph's labelled. And I'll just put that on as a dashed curve. And then what I'm going to do is I'm going to do this in two pieces. I'm just going to look at, to begin with, x minus 20. So what does cos of x minus 20 do? Well, that minus 20 is inside the function. So that means it's doing the opposite of what I expect. So this is going 20 to the right. Okay, so this is a translation by 20 to the right. So I can look at this point here going 20 to the right and this going 20 to the right. So I'm going to move every point 20 to the right. I'm just about going to fit that on, look. However, I can also see that I've got this plus 1 in here, and that means the graph is going 1 that way. So I'm going 20 to the right and 1 up. If effectively I'm translating by the vector 21. That's actually what I'm doing. So if I take each one of these points and I say, well, I'll go 20 to the right and a 1 up, and remember 1 is 1 whole square, and 20 to the right and 1 up. Okay, there we go. And 20 to the right and 1 up. And 20 to the right and 1 up. And 20 to the right and 1 up. It's just there. And I can see what my new graph looks like. Now, I've got to do this from 0 to 360. They would specify that kind of bound. So my graph comes down. It goes through 200 now. And it goes all the way back up there. Now they're going to excuse me going off here, but what they do want is the fact that this little tail is coming back down here like that. So, because we're actually looking usually between 0 and 360. So that's what our graph would look like. So that's my third example. My fourth example is going to take this and do this the other way round. The graph shows the function of y equals sine a to the x, sine of ax. Find the value of a. So what I know right now is that this is a graph. They've already given me the graphics. This is sine ax. So what I could do usefully, really quickly, is just put sine, just put y equals sine x on. So y equals sine x would go through there. It would go through 90, 150, 60, 70, 80. It would go through there. It would come down to 70. It would go through there. We'd be back at, also back at 360. Made that mistake with the 350 again, look. Okay, so here's my graph. And we go through the bottom point back up. And so what's happened to my graph? What's happened to sine x? Let's have a think. Well, this point has moved this way, and it's gone from 100. It's gone from 90 to apparently about 45 by the looks of it. This intercept here appears to have gone from 180. It appears to have gone to 90. So it appears the whole graph has compressed this way. So effectively, it's a stretch by scale factor a half. It's a stretch by scale factor a half. So this must be y equals sine of 2x because, and it's a 2 because it's the scale factor. It's inside the function because it's in the x direction. I can see the stretch is in the x direction, and we know that means it does the opposite of what I think is going to happen. So rather than this stretching and becoming double, that will produce a scale factor of a half. So that's good. So let's have a look at the example 5. The graph shows the function y equals a sine x. Well, I can see this is a stretch in the y direction, and quite clearly, if I wanted to put actually, you know what, this is incorrect, isn't it? That question's wrong. Look, that should be cos x. I'll correct that on your copy. This is quite clearly a stretch of cos x. So if I put cos x on, we can see that cos x would go through these points here. I'm just going to put that on there like that. And ignore the error there. And we can see that this has gone from 1 to 2. This has gone from -1 to -2 and so on. So this has clearly been stretched by a scale factor of 2 in the y direction. So this must be y equals 2 cos x. So I would note here that a equals 2. Up here I would have also noted that a was equal to 2, by the way. Example 6, this is a bit more tricky. I can see that this is a tan function. The graph shows the function y equals tan x plus a. Find the value of a. Okay. Right. So it would appear that this is a translation. It would appear that this translation is going to be in the x direction. That means it's going to do the opposite of what I expect. I can put tan x on to begin with. Normally what I would do with tan x is I would add the asymptotes. So we know where the asymptotes go. The asymptotes go at 90 and at 270. So let's add those to begin with, and then we can say, well, it should do this, and it should do, where's 180? There's 180. It should do this. That should be what my graph of tan x looks like. It should go through 360. It should go like that. So I kind of put tan x on, and I can kind of look at my other graph and go, well, what's happened to it then? So this point appears to have gone 10, 20, 30, 40, 50. It appears to have gone 50 to the left. So it appears what I've got is 50 to the left here. So I could say that what happens, let's consider y equals tan x plus 50. So would that cause it to go 50 to the left? Well, it's inside the function, so it's going to do the opposite of what I expect, so it's going to go left. So in this case, a could be equal to 50. So as you see, these don't take very long, but the way to do them is to sort of sketch on the graph of the original function, so I know what I'm doing. Here, the graph shows the function of cos, good, that's the right one this time, x plus a, cos of x plus a plus b. So find the values of a and b. Well, again, you just start by thinking about just cos x, and cos x goes through 80, 270. You notice I'm sketching these. Obviously, it helps enormously to have these pre-printed out if you're going to make notes on them. So here's my graph of cos x. And all I've now got to do is decide what happened to it. And the way to look at this is just to pick a point and see what happened to it. Well, if I consider this point here and this point here, I can see this point has gone 10 to the right and 1, 2 up. So I've gone 10 to the right and 2 up. So how would I write that? Well, y equals cos x, and inside the function, remember, goes in the x direction. So in the x direction, it's moved 10. And in the y direction, it's moved 2. So I know I have 10 and 2. All I've got to do is decide on the signs now. This has gone to the right. If it's gone to the right, then that must be minus 10, because inside the function it does the opposite of what I expect. And then this has gone up 2, and that's outside the function. It's in the y direction, so that must be plus 2. So I can conclude from this that a must be equal to minus 10 and b must be equal to 2.